Hi, I'm Dr. Incognito. In this video, we're going to examine some limits that require us to look at one-sided limits. So I'm going to do a couple of examples. In the first example, let's look at the limit as x goes to -5 of 3 over x plus 5. So the most elementary analysis is to simply plug the number in. As x goes to -5, this fraction goes to 3 over -5 plus 5, which is 3 over 0, which is undefined. And what's happening is the denominator is shrinking, and as the denominator shrinks, the denominator here is shrinking as x gets closer and closer to -5, as that denominator shrinks, this ratio will grow. So we expect this in a limit to actually correspond graphically to a vertical asymptote, and so we expect the answer to be either plus infinity or minus infinity. Actually, in the one-sided limits, we expect that. So the fact that we have this division by 0 tells us that the graph of the function f of x equals 3 over x plus 5 has a vertical asymptote at x equals -5. So the graph when x is -5 has a vertical asymptote. And when we're looking at here a two-sided limit, then we need to investigate the one-sided limits to see if the behavior is the same on both sides or different. So the limit as x goes to -5 from the left of 3 over x plus 5. So let's investigate this carefully. This limit is either going to be plus infinity or minus infinity. The denominator is going to 0, that's causing the fraction to blow up, but it could be a positive fraction or it could be a negative fraction. So the answer could be plus infinity or minus infinity. So we have to analyze that a little bit carefully. X is going towards -5 from the left side. So x is less than -5. So think of x as being a number like x is -6 or -5.1 if you want to make it a little bit closer. So you add 5 to that. Since x plus 5 is in our denominator, we want to add 5. X is less than -5, so x plus 5 is going to be less than -5 plus 5, which is 0. So x plus 5 is less than 0. X plus 5 is negative. So in this limit, x is going to -5 from the left. This fraction, 3, is obviously positive, and in this situation, x plus 5 is negative. So we have a positive divided by a negative, which is, of course, negative. And my choices here were plus infinity or minus infinity, so it must be minus infinity. In other words, on the left side of the vertical asymptote, the curve is going down. Now, the original problem was a two-sided limit, so maybe the answer to the two-sided limit is negative infinity. We have to check the other side. If the other side gives us negative infinity, then the two-sided limit is negative infinity. If the other side, however, gives us positive infinity, then the two-sided limit does not exist. So let's check the other side. The limit as x goes to -5 from the right of 3 over x plus 5. So in this situation, here's -5. X is going to -5 from the right. So x is bigger than -5, and x plus 5 is bigger than -5 plus 5, and that's 0. So x plus 5 is positive. So in this limit, the fraction is 3 is positive, and x plus 5 is positive. Positive over positive is positive, so my choices are plus infinity or minus infinity. So on this side, I'm getting plus infinity. And so the curve has a vertical asymptote, at x equals -5. It goes to negative infinity from the left, and it goes to plus infinity from the right. So the two-sided limit does not exist because the one-sided limits are different. If they were both plus infinity, we could say the two-sided limit was plus infinity. If they were both minus infinity, we could say the two-sided limit is minus infinity. But here we're forced to say the limit as x goes to -5 does not exist because the one-sided limits do not agree. The one-sided limits are different. Okay, so when you have a vertical asymptote like this, which is characterized analytically by having a division by 0, a non-zero number divided by 0 is a telltale sign of a vertical asymptote. And when you have such a thing, the behavior on either side could be different. It could be plus infinity or minus infinity in the one-sided limits. So you have to investigate those carefully to make any conclusions about the two-sided limit. Another example where the one-sided limits come into play is dealing with absolute values. So in this example, we'll look at the limit as x approaches 3 of the absolute value of x minus 3 divided by x minus 3. So first analysis is plug in 3, and you get the absolute value of 0 divided by 0, which is 0 over 0. And this is an indeterminate form. This is an indeterminate form. We don't necessarily have a vertical asymptote in this case. The last example, we had 3 divided by 0. If the numerator is not 0, but the denominator is 0, then you're going to have a vertical asymptote. But with 0 over 0, that's not necessarily the case. And in this case, the graph does not have a vertical asymptote. Let's analyze it. Let's look at the one-sided limits. And here the one-sided limits are necessary because when you look at an absolute value, just the absolute value of x in general is equal to the absolute value of x. Well, the absolute value of the number is just that number itself if that number is positive. So, for example, the absolute value of 5 is positive, so the absolute value of 5 is equal to 5. On the other hand, if x is negative, the absolute value of -5, that's also 5. So you have to erase the minus sign. And the way you mathematically erase a minus sign is by actually putting another minus sign in there. The absolute value of -5 is the negative of -5, which is positive 5. So if x itself is negative, the absolute value of x is negative x. So here we're looking at the absolute value of x minus 3. If x is bigger than 3, then the quantity inside here is positive. However, if x is less than 3, then the quantity inside here is negative. And so we have two cases to consider, and different things are going to happen in each case based on this definition of absolute value. So let's take a closer look. And we will do so by investigating the one-sided limits. Depending on which side of 3 x is on, we will have different results for the absolute value. First, let's look at the limit as x goes to 3 from the right. That one's a little bit easier, of the absolute value of x minus 3 over x minus 3. So x is going to 3 from the right. So x is bigger than 3, which means x minus 3 is positive. Since x minus 3 is positive, the absolute value of x minus 3 is simply x minus 3. X minus 3 is positive. The absolute value of a positive quantity is itself. And now this fraction is 1. So as x goes to 3 from the right of 1, which is 1. So a nice simple limit. Not infinity or minus infinity. No vertical asymptote here. The limit is 1. And the other side, we're going to get minus 1. As x goes to 3 from the left, since x is going to 3 from the left, we use this same diagram here. X is here. X is going to 3 from the left. X is less than 3, so x minus 3 is going to be negative. X minus 3 is negative, and so the absolute value of x minus 3 is the negative of x minus 3. So this time, you can cancel the x minus 3's, but you have a negative 1 instead of a 1. So this is the limit as x goes to 3 from the left of negative 1, which is negative 1. So again, like in the last example, the two-sided limit here, this two-sided limit does not exist because the one-sided limits are different. The one-sided limits differ, and so the two-sided limit doesn't exist. The graph of this function, if x is bigger than 3, the graph has the height 1, and if x is less than 3, the graph has the height minus 1. So it's just a horizontal line, and then you have a jump, discontinuity, and then you're back on the horizontal line again. That's what this graph looks like. There's no vertical asymptote, but when you're dealing with absolute values, the absolute value function has an abrupt, has a change in its formula when the quantity inside changes sign, and so it helped to look at the one-sided limits, and in this case we got different answers. Okay, so there are a couple of important examples where we're trying to calculate a two-sided limit, and it's a good idea to investigate the corresponding one-sided limits. Thank you for watching.